Welcome back to the deep dive. We're diving back into the world of the OEIS,
The OEIS.
the Online Encyclopedia of Integer Sequences.
Today,
We're tackling A000081.
this is a good one.
Yeah, a sequence that on the surface seems simple, the number of unlabeled rooted trees with n nodes.
Right.
But as we'll see, it's anything but simple.
What's so fascinating about A000081 is how it acts as a bridge.
A bridge.
Between seemingly unrelated areas of mathematics.
Okay.
We're talking rooted trees, yes.
Right.
But also connected functions with fixed points, arrangements of non-overlapping circles.
Circles, okay.
And even multigraphs.
Okay, before we get too far ahead of ourselves, can we refresh our memories on what a rooted tree is exactly?
Absolutely. Imagine a tree
Like a regular tree.
growing downwards from a single point. That's your root.
Okay.
Everything branches out from there.
Okay.
In more technical terms, it's a tree where one specific node is designated as the root,
Okay.
and all the connections or edges flow downwards from that point.
So it's like a family tree
Exactly.
with the oldest ancestor at the top.
Precisely. Now, A000081 tells us
It tells us.
how many unique rooted trees we can make with a given number of these nodes.
Okay.
The sequence starts 1, 1, 2, 4, 9, 20, 48, 48, 48,
Okay.
and grows rapidly from there.
I'm seeing how quickly the possibilities multiply.
Yes.
So how do circles fit into all of this? The OEIS entry mentions that A000081 also counts arrangements of non-overlapping circles.
Right. It seems bizarre,
It does.
but it highlights a fundamental principle in combinatorics. Seemingly different objects can often be counted using the same methods.
Okay.
For example, with 3 circles, there are 4 ways to arrange them without overlaps.
Got it.
The OEIS entry shows them visually. We have the double parentheses O, then we have OO, and then we have O parentheses O, and then O.
That's a fantastic illustration.
It's helpful.
Seeing those visuals really makes the connection clearer.
Good.
But I'm still struggling to grasp how circles and rooted trees are fundamentally linked. Can you elaborate on that?
Certainly. The key lies in understanding how we're counting both objects.
Okay.
In both cases, we're looking at ways to combine smaller units,
Or units.
branches in a tree, circles in an arrangement,
Okay.
into larger structures while adhering to certain rules.
Mm-hmm.
For rooted trees, it's about connecting nodes in a hierarchical way.
Uh-huh.
For circles, it's about arranging them without overlap.
Right.
The underlying structure of these combinations turns out to be remarkably similar.
So the sequence isn't just about the objects themselves.
Yeah.
It's about the underlying principles of how we combine and arrange them.
You got it.
Okay.
And this concept extends to other interpretations of A00000081 as well.
You mentioned connected functions with fixed points.
Yes,
That sounds a bit more abstract.
it is a little bit.
Could you explain what that means in this context?
Think of a function as a machine that takes an input and produces an output.
So
A fixed point is an input that doesn't change after going through the machine.
it stays fixed.
It stays fixed.
Okay. Now, A000081 also counts the number of connected functions.
see that?
Functions with certain continuity properties
Right.
that have at least one of these fixed points.
Okay, I see the connection to the idea of a root in a tree.
Right.
But how does this relate to the actual numbers in the sequence? Can you give me a concrete example?
Let's consider the case where n and 2.
Okay.
I mean, we have 2 nodes in our rooted tree.
Okay.
There's only one way to arrange these.
Just one.
One node is the root, and the other branches off from it.
Okay.
Similarly, there's only one connected function with a fixed point when we have 2 possible inputs.
So for each value of n,
Yes.
there's a direct correspondence between the number of rooted trees,
Uh-huh.
the arrangements of circles, and these connected functions.
Exactly. It's a beautiful example of how seemingly different mathematical concepts can converge on the same underlying structure,
Right.
leading to the same sequence of numbers.
That's a mind-blowing concept.
It is pretty cool. And we haven't even touched on multigraphs yet. What's the connection there?
A multigraph, unlike a regular graph,
Okay.
allows for multiple connections between the same 2 points.
Oh, interesting.
It can also have loops,
Loops.
where a single point connects back to itself.
Okay.
As 00081 also happens to count the number of connected multigraphs that have one loop and no other cycles.
Now, this connection is a bit harder for me to visualize.
Let me draw a quick example for you.
Okay.
Let's take a simple multigraph with 3 nodes.
Oh.
We have one loop and 2 additional edges connecting the nodes.
Okay.
This multigraph, believe it or not,
Okay.
corresponds to a specific rooted tree with 3 nodes.
Okay.
The loop in the multigraph actually represents the root of the tree.
Wow, that's incredible.
It is.
So even though they appear vastly different, there's this hidden structure that links them together.
Yes.
It seems like this sequence is like a key that unlocks a hidden world of connections in mathematics.
I like that.
Yeah.
A key,
True.
a hidden world.
That's what it feels like.
It is, and the beauty of the OEIS is that it provides a platform to explore these connections.
It does.
It's not just about listing sequences,
Yeah.
it's about revealing the intricate relationships within mathematics.
Speaking of revealing relationships,
Yes.
the OEIS entry for A000081 also mentions some fascinating formulas,
It does.
including a generating function
Right?
and a recurrence relation.
Yes.
Can we unpack those a bit?
Absolutely. Let's start with the generating function.
Okay.
It's a powerful tool in combinatorics that essentially encodes the entire sequence into a single function.
Okay.
It's like a mathematical fingerprint that uniquely identifies the sequence.
Okay. But how does it work in practice?
Imagine you have a magic box,
Okay.
you put in the value n,
Okay.
and it spits out the nth term of the sequence.
Okay.
The generating function is like a blueprint for building that magic box.
So like that analogy. So what does the blueprint look like for A000081?
For this sequence, the generating function involves an exponential term and a series that includes terms like ax, a by 2, a by 3, and so on.
Okay.
These ax terms represent the generating function itself,
Okay.
but evaluated at powers of x.
Okay.
It's a bit of a recursive definition.
So it's like a mathematical Russian doll, a function within a function within a function.
Precisely. It might seem complex at first,
Yeah.
but this recursive structure is incredibly useful for analyzing the properties of the sequence.
That makes sense. Now, what about the recurrence relation?
Right.
The OEIS entry mentions that it allows us to calculate any term in the sequence based on the previous one.
Exactly.
So like the one before it.
The recurrence relation for A000081 tells us how to build the sequence step by step.
Okay.
It gives us a formula to calculate the n plus 1th term using the values of the previous terms, a1 up to an.
Okay.
This formula involves a couple of sums
Mm-hmm.
and uses the divisors of the index n.
Divisors, those are the numbers that divide evenly into n, right?
That's right. For example, the divisors of 6 are 1, 2, 3, and 6.
Okay, so the recurrence relation gives us a recipe for generating the sequence,
Yes.
one term at a time.
Uh-huh.
Are there any practical advantages to using this recipe over, say, the generating function?
The recurrence relation is particularly useful for computing the terms of the sequence,
Okay.
especially for larger values of pound.
Okay.
It can be much more computationally efficient than using the generating function directly.
So it's a trade-off between elegance and efficiency.
It is.
The generating function gives us a compact and elegant representation,
Right.
while the recurrence relation provides a practical way to actually calculate the term.
You've summed it up perfectly.
Okay, good.
It's like having both a blueprint and a set of instructions for building our magic box.
This has been an incredibly insightful deep dive into A000081.
I agree.
It's remarkable how a sequence that starts with counting rooted trees can lead us to such diverse and interconnected mathematical concepts.
It really is a testament to the beauty and interconnectedness of mathematics.
Right, and while we've explored a lot of theoretical ground, it's important to remember that rooted trees have real-world applications as well.
Oh, absolutely.
Earlier, we touched on how file systems on a computer resemble rooted trees.
Yes,
Are there other examples where this structure pops up in practical settings?
definitely. Think about decision trees used in machine learning,
Uh-huh.
or the hierarchical structure of organizations and companies.
Mm-hmm.
Even the way we represent phylogenetic relationships in biology often uses a tree-like structure.
So these abstract mathematical concepts we've been discussing actually have tangible connections to the world around us.
Exactly, and that's what makes exploring the OEIS so fascinating.
Yeah.
It allows us to see the hidden patterns and connections that underlie so many aspects of our lives.
Absolutely.
It's like having a secret decoder ring for the universe.
I love that analogy. It makes me wonder what other secrets might be hiding within the OEIS waiting to be unlocked.
That's the beauty of it. There's always something new to discover.
Yeah.
Each sequence is a doorway to a world of mathematical wonders.
Well, before we get lost in the vastness of the OEIS,
Okay.
let's bring our focus back to A00000081.
Sounds good.
Is there anything else in this sequence's entry that you think our listeners would find particularly interesting or thought-provoking?
Well, there's one more thing I wanted to touch on.
Okay.
The OEIS entry mentions a connection between A000081
Huh?
and something called planted trees.
Planted trees. Okay.
Mind shedding some light on that?
No, not at all.
A planted tree is essentially a rooted tree with a very specific condition. The root node has a degree of 1. This means it's connected to only one other node.
Okay.
Imagine a tree with a single, very short trunk.
I see. So it's like a rooted tree, but with a bit of extra constraint.
Right.
What's interesting about these planted trees in relation to our sequence?
What's fascinating is that the number of planted trees with n+1 nodes is exactly the same as the number of unlabeled rooted trees with n nodes.
That's a surprising connection. I wouldn't have guessed that there would be such a direct relationship between the two.
It's a subtle but beautiful link.
Yeah?
You can almost think of it like adding an extra node to the top of each rooted tree to create a planted tree.
Right.
It highlights how even seemingly minor modifications can lead to interesting mathematical relationships.
This whole deep dive into A000081 has been a revelation.
It has.
We started with what seemed like a simple concept, counting rooted trees,
Right.
and ended up exploring a web of interconnected mathematical ideas.
It's true.
Circles, functions, multigraphs, planted trees.
Yeah.
It's amazing how they all tie together.
It really speaks to the power of sequences like this one.
It does.
They're not just lists of numbers.
Right.
They're keys that unlock hidden patterns and relationships within mathematics.
I think our listeners are probably feeling a bit overwhelmed with all this information.
A little bit.
In a good way, of course.
Of course.
If someone wanted to delve deeper into A000081 and explore some of these connections on their own,
Yeah.
where would you recommend they start?
The OEIS entry itself is a fantastic launching point. It provides links to relevant research papers, references,
Yeah?
and even code examples for those who want to get computational.
Right.
From there, it's all about following your curiosity.
Do you have any parting advice for our listeners as they embark on their own mathematical adventures?
I encourage everyone to approach mathematics with a sense of wonder and playfulness. Don't be afraid to ask questions, explore different perspectives, and search for those unexpected connections.
Okay.
You never know what amazing discoveries you might stumble upon.
That's great advice.
Thank you.
I think it's safe to say that we've all gained a newfound appreciation for the beauty and complexity hidden within the seemingly simple act of counting trees.
I wholeheartedly agree, and who knows, maybe
Right.
our listeners will be inspired to submit their own sequences to the OEIS one day,
That'd be great.
contributing to this ever-growing tapestry of mathematical knowledge.
That would be fantastic.
Oh.
And with that, we've reached the end of our deep dive into OEI sequence I000081. We hope you've enjoyed this journey into the world of rooted trees and their fascinating connections.
Until next time,
Keep exploring.
keep diving into the incredible world of mathematics.